Section 3.4, derivatives are combinations of functions. The derivative of functions, we have learned just a handful of functions, how to take derivatives of them. But what if you have a bunch of stuff, say, added up or subtracted or whatnot? Then what? So the way we handle it is figure out how all that works out. And once we have a bunch of reasonable rules, then we can work out a lot more functions than just the basic ones like the derivative of sine x or the derivative of x squared. Because that way we want to be able to do, say, x squared plus 5x. What is the derivative of that? Now, before we do that, I want to mention a quick principle, which says that if f is differentiable at a, then f is continuous at a. In other words, differentiation is a much more powerful requirement than continuity is. Although continuous functions are often drawn as a smooth curve like this is actually a differentiable function, because a continuous function that can be have a ton of sharp points and is still continuous, but it is not differentiable at any of the sharp points. And of course, if a thing isn't continuous, then for sure it's not differentiable. But anyway, in order to prove that if a function is differentiable, then it is continuous, what we do is it goes something like this. Let's say we calculate the limit as t goes to a of f t minus f a. If this limit exists and goes to 0, then it would mean that the function f is continuous. And right now we assume that function f is differentiable. Now with that assumption, we can write this. So then that equals to the limit of ft minus fa divided by t minus a times t minus a. Now that seems like a waste of time. Why are we dividing and multiplying? That's because this particular thing right here is the definition of derivative. This means this equals, being the f is differentiable, the limit of this thing exists. And also a limit of a product is the product of the limits. So we can calculate limit of each one individually if it exists. And therefore, the limit of this thing exists, and they equal to f prime of a, which means the derivative of f at a times the limit of t minus a as t approach a. And that, of course, equal to 0. So f prime, this equals f prime a times 0, and that equals 0. So the limit as ft minus fa as t goes to a is equal to 0, which means ft approaches fa, and therefore f is continuous. So that's a very quick proof of why when something is differentiable, it has to be continuous. The next thing we want to say is that when you take the derivative of two things added together, it's the same as just to take the derivative of each and then add them up. So that's what you would expect from it actually works. To write it in symbols, we say that if you have two functions added up and you want me to take the derivative of the two functions at a point A, that's the same as simply doing each, okay? Equal to f prime of A plus g prime of A. And the reason for that is because the definition of the derivatives. That is, if we're calculating this one, how do you prove this? You just go back to the definition, which states that, for example, what is that? That the limit of two functions added together is okay, as defined by the derivative is simply f plus g of a function, say t, okay, minus f plus g of a is divided by t minus a as t approach a. Now this particular thing can be easily split up into two functions of limits. That's the limit of each individual ones. That is, we'll do f first. So that is f of t f of t and then f of a, because f plus g of t is just the f of t and g of t. So you can just split it up, minus f of a. Notice this is the function notation. That means the two functions are both evaluated at t. So then this is divided by t minus a. And then plus the limit of gt minus g of a. And t minus a, both going, t going to a in both cases. So then when you have that, then this of course is the definition of f prime of a, and that is the definition of g prime of a. So that's how you know that to take the derivative of a bunch of stuff, all you need to do is take the derivative of each. That seems quite obvious, but that doesn't all work. That doesn't work with multiplication. There's a different rule for multiplication because the split here isn't as nice or neat in multiplication. But we're right now in addition, and the split comes out very nicely, as you can see. And similarly, for this reason, the derivative of CF, that is, if you take a constant times a function, that's the same as simply take the constant out. The proof is very similar, because if you have a c here in the limit, all you need, you can take a constant out of a limit and not change anything. So that's why this works with a constant as well. And for this, because of that, then we have the subtraction works the same way. That is, if you have two functions subtracting each other, evaluated, and you need to take the derivative, it's the same as the function, each one taking, you calculate the derivative of individual ones and then just do the subtraction as you would like it to do. Now, as an example of all this stuff, let's say we have to calculate, say k of x, quick easy example, equal to x squared, okay, plus sine x. What is k prime? That is, what is the derivative of x? The derivative is, you follow the rules. First, this one, the derivative of x to the power n is, this must be memorized, is okay, the derivative of x to the power n is nx n minus 1, which we did earlier in a previous video. So then you take this value up here and drop it down here, and then reduce 1 in this value. So that's just 1. You don't have to write 1 down. And then the derivative of sine x is equal to cosine. That's a very quick and easy memorize. So the sine x becomes cosine x, and that is your answer to what is the derivative of k of x is. As we have shown it, that the derivative of a sum of stuff simply means you take the derivative of each individual one and add them up. So it comes out very nicely. And it would have been the same if this was a minus. In the next video, we'll do the multiplication and division, which is slightly more complicated.